hope every... Okay, thank you very much. I hope everyone can understand me very clearly. So it's a pleasure to be back, and it's of course also very unusual place for TRR seminar here in the deep south of Germany, but it's very pleasant here, and I can only recommend all of you to visit Marcel here. Around the corner of the university, there is a nice beer garden. Okay, in my talk, I'm going to talk about machine learning and how we can use this to identify or detect causality relationships. That's
Jan, sorry, but could you maybe move a bit closer to the microphone?
Yes, okay.
Thanks.
Now I'm in front of the microphone. So that's work in collaboration with UN and Sun Tao Fu from Peking University, and most of the work was actually done by you here. Okay. Okay, causality. That's of course a very important aspect since we look at complex systems, and we of course want to know whether one forces or event causes some other events. And you probably all wonder whether there might be some relationship between the number of sharp attacks and the number of ice cream things. So of course there's the big question whether if we have increased number of sharp attacks, whether this will drive high ice cream sales. And I will come back to this in the end. The causality, maybe here just maybe this might be something very basic. That's of course what we want to understand, the influence by which one event, process, or usually called the cause, contributes to the production or emergence of some other event or process, the effect. But this cause is at least partly responsible. So of course we usually deal with very complex systems. So there might be the many different causes which interact, but of course we typically want to identify at least some fundamental causes on some effects. And the effect is partly dependent on the cause. So that's what we basically want to identify, and that might then lead us to better understand this complex system, say the climate system, and which might then allow us to make more skillful predictions. So in general, this process or event has many causes, which are also said to be causal factors for it. And they lie in the past because then they can cause something which happens in the future or in the present. And this effect can then also be then a cause which causes some other effects in the future. So that there might be some lack relationship. And that's also something we try to identify here. So if a standard approach of looking at those relationships is of course looking at correlations. But we probably all heard that correlation does not imply causation. So but many studies they look at correlations. I mean, that's also very powerful and very easy to compute. Whatever all those other causality methods I talk about, introduced here, they are typically much more complicated to estimate, to compute. So just looking at correlation coefficients, that's typically relatively easy. So that's typically we look at the Pearson correlation, that's the expression for this. And strictly speaking, that's only a good measure for linear systems where you have Gaussian distributed white noise. Only then, basically, this correlation value makes really sense. So if we just look at the point clouds, then you can see how strongly the correlation value is. So if this is very much on a straight line, plus or minus 1, if it's very much almost uniform or, I don't know, circular distributed cloud points, then it's basically uncorrelated. But even if you have these straight lines, you can basically also get zero correlation. So just having this very fine relationship doesn't really tell you much about the underlying dynamics, especially if we go to nonlinear systems. All those structures here have zero correlation, but then at least here this one and others here, you might think they might have some underlying nonlinear causal relationship. So that's why the Pearson correlation coefficient is not a very good measure for many systems. We also demonstrate this here for those systems. So we have here linearly coupled system. So here that's the A variable basically. So theta is white noise forcing. So that's just looking at A would be a damped oscillation, and B also has this damped oscillation component, but it's also coupled with A. So that would be, so in this sense, A would cause or influence B. And if we just look at the Pearson correlation coefficient, then basically we see there is some causal relationship or at least some significant Pearson correlation value. If we look at the similar system and just make this nonlinear, so we have here x times x, y times y, and y times x, and here the Pearson correlation coefficient basically is non-significant. So for if you know your system is linear, you might get away with Pearson correlation, but once it becomes non-linear, you might be in trouble by relying on the correlation coefficient. So the next step in causality methods is so-called the Granger Causality. It was developed by Clive Granger, who won the Nobel Prize for related, I think also for this, but also for other things he worked on. And here we basically, that already introduces the concept of predictive skill. So we don't just look whether things are correlated, but we look whether if we add some further variables, whether they actually might improve the predictive skill. And for Granger causality, what one does is basically look at autoregressive processes. That's basically the form written down here. And then one can then identify if one would have the this coefficient matrix. If we have here also more than two variables, then we could have with a higher dimensional coefficient matrices and then basically see whether those interactions contribute to predictive skill or not. So that's, but again, that's mainly something which works for nonlinear systems. So the idea here is, so we have the x variables and times here, we have a peak here, and that would then try this peak here in the y variables in those two situations. As if we include x, knowledge of x for predictions of y, that would increase the Granger causality, and then we would claim there might be a causal relationship. So that also has been applied for climate data sets. So here the relationship between ENSO, which is an important mode of climate variability in the ocean, or the coupled atmosphere-ocean system, which also affects global mean temperature. So here in the upper plots, that's just the lag regression, just Pearson correlation coefficient, and here the Granger causality. And so looking at the relationship that the ENSO causes surface temperature to fluctuate, that whatever is spread here, basically there we have significant correlation, or whether the surface temperature would kind of try ENSO. Then we kind of know from physical understanding that that's actually not the right relationship. ENSO causes fluctuation in surface temperature, but not the other way around. So again, here an example where looking at linear correlations would give you wrong impression about causal relationship. But if you look at Granger causality, we see here this relationship that ENSO affects surface temperatures, but then the other way around, surface temperatures affecting ENSO. That's only very few areas here where you might have a significant grid points for this relationship. So now we want to also deal more with nonlinear systems, because most of the complex systems we deal with are nonlinear, and there is this method Convergent Cross Mapping, and that's kind of based on dynamic resistance theory, and is based on Tarkin's embedding theory. So that's basically, if we have a complex system, but we only have partial observation, then we only have one observed variable or just one grid point, and now if we basically embed this time series, so basically we'll take the value at time t minus 1, t minus 2, and basically reconstruct the state vector in that way. And Tarkins basically proved that by doing that, you can basically reconstruct the attractor. And that's basically the idea behind the convergent cross mapping, that we basically take those, say we have two variables, we want to see whether they have a causal relationship. So we take those two and basically take each to reconstruct the attractor, and then basically see whether there would be nearby points at the same time. And then we basically would then look or come up with some correlation measure, and then we could claim whether there is some causal relationship. Okay, here is illustrated for the Lorentz 63 model. Here we see this attractor of the Lorentz 63 model. And then we basically, so we would have x, y, and z variables with dimensions. And here we just take the x variable, and then we basically do this embedding xt minus 1, xt minus 2, or minus tau minus 2 tau. And the same here for the y variable. And then we look here at a certain time, and this we would be located here, and then we can see in this area around this point. But the same for the y variable. And if those points are then actually close by at the same time, that would then indicate that there might be a causal relationship. So that's the idea behind convergent cross mapping. So let's see that here our variable x, variable y, and basically whether we can infer from x basically the value of y at either at the same time or future or past. So whether this would be the cause or effect. So the leg basically would then tell us something about whether x causes y or y would cause x. So we have here our observation time series, then we would do this cross mapping, this phase-based reconstruction. That's usually, or this method is called empirical dynamics model, which basically does this. So we will have our estimated value, then we basically can see how close this is actually to the observed or to the real value. And then basically we can compute time lengths, the CCM coefficients with the correlation measure. Okay, now just to demonstrate this at one of the earlier examples with the linear system, nonlinear systems here. Then, if you remember, the correlation basically showed you lots of oscillations for the linear system and basically no significant correlations for the nonlinear system. And here we basically get a much cleaner picture, so that we kind of see that we first try to do A X map B, so we construct A for B or B X map A, so to see causation and response, so that then we look for the maxima of the correlation coefficient. So that's what that also indicates something like the lag relationship between those responses, and you can also see that the causation is the blue line, so B X map A, so A causes B as it should be, and the red line would be then the response, because here the maxima would be a positive length, and if it's the cause, that should be the maximum should be at the negative. And in the nonlinear system, then we also basically just see here this causal relationship with the maxima at negative lengths. Then we can also look at much more complicated models, the Lorentz 96 model, which is a much higher dimensional model. There we can also change the coupling strength between the two variables, which are displayed here, X and Y, so X1, X2, 1. So there are many XY points and many Y points. So that would be with strong coupling. So if we just look at the Pearson correlation coefficient, you see here significant correlation. And again, with the CCM, we can identify cause-response relationships, which are also everything above the dotted area here is statistically significant, and everything outside of this dashed area here is also statistically significant. Then we can do this for recoupling between those two modes. So the Pearson correlation coefficient basically is not significant any longer, but we can still see some indications for the CCM coefficients that they're statistically significant, but now we get a more complicated structure. That we have here causation, but then also negative or positive length for both ways. So that might be, so on one hand, you could say that in this model we have strong wave dynamics, that we have some, in this mode, some wave, which then might also trigger the same mode response later on. That would be one possible interpretation. And this also has been applied to climate data, just here this study by Wang et al., where they look at the relationship between soil moisture and precipitation, and they also find lots of areas where there is this causal relationship. Okay, so CCM is already a very powerful method, but the space-based reconstruction has a couple of disadvantages. So first, it's very computationally very expensive, and it's also very sensitive to noise, which I will also demonstrate later. So that's where we then started thinking about whether some machine learning algorithm might actually be better than. And there is something called reservoir computing, which has been shown to be actually very good for representing dynamical systems. So that's kind of a framework from the current neural network theory. So basically, reservoir computing maps some input signal into a higher dimensional computation space to some nonlinear system, this reservoir. But the dynamics of this reservoir are fixed, so that makes it relatively computationally cheap. And this reservoir is also kind of treated as a black box. So the first benefit of this framework is that training is actually performed only at the readout stage, as the dynamics are fixed. But that's, of course, the advantage that it's basically relatively cheap to do them. And another interesting point is actually you could also have a physical reservoir. So you could actually build your own. You don't need a computer. So you could have some other system which basically could do this for you, which I thought very neat property. So just to illustrate this maybe with this schematic here, so we have here our input data. So basically we project this into this reservoir, into those neurons. Then we have this quick out stage, which then basically we hope that we get our reconstructed attractor or phase space structure here. So the major advantage is that it's very fast, which I also have later a slide comparing this with CCM, and it's also you don't really need so low training costs. So you also don't, I mean, CCM would also require you to have a huge amount of data, and here you can get away with less data. So that's what we two very attractive properties. So how do we do this now? Now say we have two time series where we want to see whether there is a causal relationship A and B. So then we basically put this into this reservoir computing to basically predict whether we can use A to predict B or B to predict A. Then we evaluate this with the original time series, and then basically we look at the correlations and then compare the optimal lengths. And then that would be our measure whether that would be a causal relationship or not. Okay, so again, here we start with a simple linear system driven by additive white noise, and B would then be as a causal relationship with A here. And you can so on the top that's reservoir computing, and on bottom that's the CCM. And you can see for the linear system, both of them produce relatively similar results. If we now go to nonlinear systems, then we have here two different ones. Here this one where we also can vary the coupling strength. So this here would be with a strong coupling, with a weak coupling. So that's again reservoir computing, here convergent cross mapping. And again you can see both or the RCC performs somewhat better than especially here. So here, CCM, everything is for this direction is not significant. There's RCC, they find this response, but they both find always the causal relationship and maximum of the length of negative length. Then we can also say here this cross interactions. X is also forced by Z and Z is caused by X. But then both methods kind of also work relatively well here. So that's of course and also encouraging that also this machine learning approach where we actually know much less about what it is actually doing with CCM. I think we have a very nice intuitive understanding why this actually would provide us with some causal relationships with machine learning, because there's always this black box that's much less obvious. Then we also wanted to see whether if we have a delay effect in this causal relationship, so that we now have here time t minus tau, and then we vary tau for different values. And if we do this and look at the causal relationships, then we also see that this peak basically also moves accordingly. If we increase this tau, so we have larger length, then also the maximum of this causal relationship occurs earlier or at larger negative values. Then one motivation was the effect of noise on most of those phase-based reconstruction methods, and to see whether reservoir computing performs better. So we basically then just added random noise to the system, so 4% and 40%. And in those figures here, the dashed line, that's always the system or the causal relationship without noise. And then we have here for 4% and for 40%, again, reservoir computing on top, and convergent cross mapping on bottom. For 4%, both kind of still perform relatively similar and relatively well compared with the no noise situation. But if we then increase the noise much more, then we also see that reservoir computing performs better. Then we can also look at the prediction skill and the amount of noise. And then here for reservoir computing, we measure basically the predictive skill by this relative deviation, by this expression here. And you can see that those deviations, if we increase the noise for reservoir computing, stay below those for convergent cross mapping. And also, if we look at the peak position, that's also relatively better extracted by reservoir computing than convergent cross mapping. Then, if you look at, let's say, something one could maybe call remote interaction, here again, the Lorentz 96 model, that's basically the equation of the Lorentz model or the version we use. And here is the schematic of how it actually looks like. So we have here this circle of the X modes, so which basically you can then imagine we might have some waves propagating here, and each X mode is coupled to Y modes. But then one can, of course, then also look if we have better some fluctuation in X1 would then maybe cause some fluctuation at the Y5 mode also. And then we can also then look here at the causal relationships, and basically we can also identify this propagation of the signal of the wave motion, how it basically then affects this remote location. So that basically here if you then look at different modes of X and Y, that also then basically this maxima basically also moves in time closer to when we basically see the signal or the effect in this mode we are interested in. So that's of course also very nice property. So this slide just to demonstrate that reservoir computing, of course, also has a couple of parameters we have to choose. One is, of course, the number of the neurons we have in our reservoir, and then, of course, the spectral radius for this embedding or this measure. But the point here is, of course, there is some variation, but the location of the maxima is typically relatively the same. So in that sense, using this for this causal relationship identification is relatively insensitive to the exact model setup. Now, for the coming towards the end, just to also show you that we can apply this to some observed data. So we looked at the Stratosphere-Troposphere Coupling, looking at the Arctic oscillation. That's a large-scale pattern with the center of variability over the Arctic and in the mid-latitudes. So that also occurs at different vertical levels in the atmosphere. So we have here time series at 1000 hectopascal, which is close to the surface, 150, which is close to the tropopause, and then we have 3 time series in the stratosphere going even further up in the atmosphere. Then we can first look at the Pearson correlation coefficient, and basically we see this correlation between different levels kind of almost at like 0, which, because we know there is actually a downward propagation. So that's something like here, which also occurs over a period of time. So that already would also be misleading, that there's actually some kind of instantaneous signal. If we now look at first here, convergent cross mapping, we kind of see here time like in days. That is actually this downward propagation actually takes a couple of days, which is also what our dynamic understanding tells us. Then we can do the same with reservoir computing, that we see also similar behavior, so basically this downward propagating. So that's also just to demonstrate, I mean, that's scientifically probably not that exciting since we kind of understand what dynamically is going on there, but that's just to demonstrate that with reservoir computing or convergence cross mapping, we actually can also identify those causal relationships in very high dimensional, very noisy data. So just here, computational speed. So that's, you did this, I think, on a laptop with a 3.6 gigahertz CPU, but I guess probably would be relatively similar on some other computers. Say for given time series of 10,000 data points, reservoir computing would do this in about 90 seconds. For convergent cross mapping, you would take 10, 15 times longer. So that's, of course, one of the main advantages of using this machine learning approach compared with convergent cross mapping. And of course, it's much less sensitive to noise, which probably is also very important. Then another, maybe just the brief remark, transfer entropy, that of course would be also a very powerful tool for causal relationships. That of course also works, but it's even more data intensive and computational intensive. So that's might, on conceptual level, that might be much more powerful because that really tells us something about causal relationships, but computing this is, of course, relatively expensive, also data intensive. Okay, coming back to this original question I posed, do sharks actually increase high ice cream sales? The answer is, of course, because they like ice cream. Okay, just to summarize, so I introduced certain methods or a couple of methods for causal mechanism identification. One was this convergent cross mapping, which is also applicable to nonlinear systems compared with Pearson correlation or Granger causality, or this machine learning, reservoir computing causality. And they both work relatively well also for complex systems. They can also detect lack causality, but reservoir computing has some advantages. It's computationally much more efficient, much more robust against noise in the time series, and can also be applied in a probably more seamless way to high dimensional data. And I also successfully applied this to Stratosphere-Troposphere Coupling. So if you want to read more, then we publish this in 2 papers in chaos and climate dynamics. But I'm also happy to answer your questions. Thank you very much for your attention.